Okay, I can start whenever you like.
Okay, so let me introduce you. The next speaker for today's session is Professor Tane Vergili. She is from Turkey, from Karandiz Technical University, and her talk is Proximal connectedness, spatiality, and descriptively connected space. You are welcome.
Okay, thank you very much. This is a joint work with Professor James Peters from the University of Manitoba in Canada. And in this talk, I would like to give a brief information regarding an ongoing project. As a matter of fact, Professor Peters is giving the next talk, and I strongly believe that he can cover anything that I might have missed. So we know what a topology is, and we know that there are some other ways to construct a topology on a given set. So we start with a set X together with a nearness relation between its points and subsets, satisfying the following conditions. So no point in X is near the empty set. A point that is in a set B is near B. A point is near the union of two sets if and only if it is near at least one of them. And if a point X is near the set B, and if every point of B is near the set C, then X is near C. So in that case, one can define the closure of a set, which consists of all elements in X near B, and then one can define a topology on X by declaring that a set B is closed if and only if it is a closure, it is equal to its closure. So this is a nearness of a point to a set, and now we will discuss its transition to nearness of two sets called proximity. Let X be a non-empty set and A and B its subsets. We denote the nearness relation by delta, and the notation A delta B means that A is near B. And obviously, proximity gives rise to a topology when the first set is a point or a singleton set. So before giving the axiomatic construction of proximity spaces, let's consider this picture. If we look at this black and white picture, we see that the visual subsets A and B are removed since they have no points in common. Nevertheless, the subsets B and C are near since they have points in common. So we can provide another example. Given a metric space, one can define a nearness relation on its subsets by declaring that two subsets A and B are near, provided their Hausdorff distance is 0. And this example provides a motivation for the axioms of a proximity space, where even X may not be a metric space. So we have a non-empty set X together with a relation delta on the collection of its subsets. If delta satisfies the following four axioms, then a structure set X delta is called a proximity space. The first one states that all non-empty subsets are removed with the empty set. The second one states that the nearness relation should be symmetric. The third one states that the intersecting subsets are near. And the last one states that if a subset A is near to the union of B and C, then A is near to at least one of B and C's. For example, if you have a topological space X, then you can define a nearness relation on its subsets by declaring that two subsets A and B of X are near, provided their closures overlap. So now by this construction, you have a proximity space, and this relation satisfies the requirements to be a proximity. We can also construct a new proximity space from old ones. If we have a family of proximity spaces, then one can define a nearness relation on the Cartesian product of the members of this family and declare that two sets are near, provided their ith projections are near in the corresponding proximity space. If we reconsider the same picture, we notice that A and B are spatially removed, but they contain points with the same gray level intensity. So even these two sets are removed, they have points that have equal descriptions. And this is the motivation for defining a nearness relation in terms of features describing a set. What do we mean by saying an equal description? Given a set X, a probe function is a scalar function, phi from X to R. So here phi of P may represent a feature of the point P, such as gray level intensity, color, or texture. Then uppercase phi is the collection of probe functions, so that uppercase phi of P denotes a feature vector containing members representing feature values extracted from P. And for a subset A of X, uppercase phi of A is the set of vectors of real values that describes A. Then we could say that two subsets A and B are descriptively near, provided their descriptions overlap. So if we look at the same picture on the left, and if we assume that we have a probe function on this image, which represents gray level intensity, then A and B are descriptively near, since they have some pixels with equal gray level intensity. Nevertheless, A and C are descriptively remote, since all pixels in C are black, while A has a gray level intensity greater than 0. So on the right side, there is a sample of an fMRI brain video frame. So you can see mainly orange voxels, which tell us the region of the brain that are active at the same time. So we notice that the orange regions are spatially remote, while they are descriptively near. As a result, we can consider this picture as a point cloud to get a reasonable information by using computational proximity methods. Similarly, to define a descriptive proximity space, we need a probe function on an unempty set X, and then we are looking at the descriptive properties of the subset of X. And all the axioms for descriptive nearness relation delta sub phi are obtained by swapping out nearness relation delta with delta sub phi. So here the descriptive closure of A is the set of points that are descriptively near A. And then we can also define a topology on X by declaring that a subset A is closed, provided it is equal to its descriptive closure. Now let me introduce continuity for proximity spaces. A function f between two proximity spaces X and Y is proximally continuous, provided f maps two near subsets in X to two near subsets in Y. And a map between two descriptive proximity spaces X and Y is descriptive proximally continuous, provided f maps two descriptively near subsets in X to two descriptively near subsets in Y. So the concept of connectedness in topology can be also adapted to proximity spaces. So given a proximity space X, two of its subsets A and B are said to be delta connected if there is a sequence of subsets of X starting with A and terminating at B in such a way that each consecutive pair of the sequence are near. If every pair of subsets of X are connected, then we say that X is a connected space. And we know that connectedness is preserved under a proximal continuous function. What we stated for connectedness in spatially proximity space is also valid for descriptive proximity spaces. We can introduce delta sub phi connected subsets. We can introduce descriptively connected spaces, and then we can show that descriptive connectedness is preserved under a descriptive proximal continuous functions. Now, let me explain how the idea of proximity spaces can be considered for digital images. A digital topological space X is a subset of Q times Q, where Q represents the set of the rational numbers. We call each point P in X a picture element, and a picture element with integer coordinates is called a pixel. A picture element which is not a pixel is called a subpixel. For example, a pixel P at location XY in a digital topological space is identified with an area of the plane bounded by a square with size of length 0.5, and the pixel is nothing but the centroid of that square. So the boundary of a pixel is the set of all picture elements in X, whose components differ with the components of that pixel from 0.5. Then we say that two pixels P and Q are adjacent, provided they intersect along their common boundaries. So in this picture, the gray pixel and the red pixel are column adjacent. The red pixel and the yellow pixel are row adjacent, and the gray one and the yellow one are diagonally adjacent. Then a digital image on X is a map image that is a real valued function on X. For a pixel P, the image of P is the average value of that square. And further, one can restrict a digital image to a subset of X so that the restricted map on that subset is called a subimage. Given a time parameter T, let's image sub T denote the digital image captured on X at time T. Therefore, we can consider a collection of digital images over a given time period, and that collection will constitute a video on X. A pixel at an instant time is called a voxel, and in other words, a voxel P may be represented by a triple X, Y, and T, so that the first two components show the location of that point at an instant in time T. And also, if A is a subset of X, then each restricted map, img image sub T to A, is called a subframe. Now let's define some nearness relations on a digital image. Below there are three nearness relations, but of course one can introduce different types of nearness relations if necessary. We say that in a digital image, two sub-images are near if they have pixels in common. And this nearness relation is called a discrete proximity relation. If A and B have a common pixel or adjacent pixels, then we say that these sub-images A and B are adjacent. And it is also possible that two sub-images have no pixels in common, nor have they adjacent pixels, but instead they are at maximum distance of epsilon. In that case, we say that A and B, these two sub-images A and B, are epsilon near. So this picture is from my campus. As sub-images, the car with the tree in front of it are near. The two bushes on the left are adjacent. And the car and the tree at rear are epsilon near once you take sufficiently large value of epsilon. Now let me define connected sub-images. A sub-image is connected, provided for each pair of distinct pixels, P and Q. There exists a sequence of pixels in E, such that each pair of consecutive pixels are adjacent. And in this picture, for example, the ladybug is a connected sub-image. So we know that since continuity preserves the adjacency, we can immediately conclude that connected regions are preserved under a continuous digital functions. Now let's consider a collection of video frames over a given time interval. Given a sub-image A of X, let A sub T denote the position of A at time T. So during this video, two sub-images may overlap temporally. And in that case, we say that two sub-images are temporally near. So for instance, so imagine a surveillance camera at a fixed position showing traffic. So we observe that the images of two cars approaching each other from two opposite sides will overlap over a short period of time, and then they will move away from each other. So these two sub-images will be near temporally. And also, if the sub-images are at maximum distance of epsilon over a temporal period of the video, then we say that they are temporally epsilon near. So we know that temporally nearness relation and temporally epsilon nearness relation are preserved under a continuous map. And here is an example. So in the first row, you see the collection of video frames captured at different times. So the bus is moving rightwards, and after some time, while it is passing next to the lamp pole, the bus and the lamp pole become temporally near, but later the bus moves away from that pole. So here the pole is a background object since it never changes its position, and in contrast, the bus is a foreground object. So the bus appears in the first frame, but it disappears in the last. So if one can record its lifespan, I mean the time interval that the bus survives, and during that time period, the bus became temporally near with that pole. We can also compare two foreground objects as the video frames at the bottom row. The car and the bus have overlapping lifespans, and they became temporally near over some of their common lifespans. So the time period between the appearance and the disappearance of a sub-image is called the lifespan of that sub-image. And if two sub-images have common lifespans, so if two sub-images have common lifespans, then temporal discrete proximity implies temporal epsilon proximity. So this is an ongoing project, and it is also new to me. I think it's better to end at this point. Here are the references of my talk. And I would like to conclude my talk by sending my regards to the Ukrainian people. And I would like to end with a quote from Atatürk, the father of Turks, where he said, peace at home, peace in the world. And I hope that very soon Ukraine will find peace and calm in your beautiful country. Thank you very much for your listening.
Okay, so thanks a lot for a fascinating talk.